Yay. This is what I do in the evenings. I make videos. It's kind of fun, but all right. So let's see. Sorry, that was loud. I kind of skipped over, you're not aware because you don't know what order I made these videos. I kind of skipped over 3, 2, and 3, 3. I've never been, I don't know. So what I'm going to do, because I don't know, they're just kind of weird standards, if you will. I'm just going to go to the PowerPoint and kind of see what I have here. Okay. And that's what we're going to do together. And I'm just going to go over some things with you. All right. So my brother just texted me. My phone's going to ding again in a minute. So I'm going to go here. Here. Hope you guys are doing well. Oh, there's some of your names. And if I go here, I can go to Unit 3 PowerPoint here. Okay. So 3, 2, and 3, 3, you know, I definitely don't want to just skip over anything, but I've already done this gas laws here. But I think that there's just not too much to talk about and not too much to do, but I don't want to skip over it. I'm sorry if that's making you sick. Okay, we would kind of start here because those are your IMFs, and this would be after IMFs. I've already talked about that. Conducting electricity when the electrons are mobile, right? When melted or dissolved in water or another solvent. Okay, so what we have here, and let me see if I can, I wonder if my like pink might write on here. Yeah, good. Okay. So 3, 2, I think might be types of solids. I don't know, but I hate to just skip this. So there's something called covalent network solids. Okay. They are extremely hard. You're talking diamond. Think of diamond as like the hardest substance. Earlier at one lesson, I had said something, this is like material science. You know, what's the best material to use for your certain purposes, you know, for your needs. And you have to understand, does it rust? Does it melt? Does it dissolve? What's its boiling point? What's its freezing point? Right? Is it hard? Is it malleable? Do it bend? So covalent network solids are really hard. And here you see, it says diamond. And what you have is a 3-dimensional network. So you could imagine like carbon in every direction attached to like another carbon. I can't draw 3-dimensionally. Carbon, 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 carbon. And this goes on, actually, I could pull it up, would be more effective, with this intricate network of covalent bonds to where there's not a piece, like there's not a bond, there's not a molecule. It's just, oh, this is a great example. It's not just one molecule like this, but it's a gazillion molecules stuck together. So they're covalently bonded, they're really tight, they're not coming apart, as opposed to just my one molecule, where I could have many of these molecules, but these molecules are covalently bonded to each other. Right? The molecules are covalently bonded to each other. So, or the atom. It may just be an atom. It may be a pure substance like diamond, it's pure carbon. But each carbon atom is literally covalently bonded to a network of other carbon atoms, right? Like this. Oops. Right, like everything is attached to everything else, you know. I'm kind of losing it here. He's attached to him, attached to him, attached to him. And there's, you know, everybody is, it's really, and it's stronger. Like there's probably something here too, to be honest with you. because it's so strong. Okay, so I'm going to leave it at that. Silicons, as you see, silicon dioxide and silicon carbide, those as well as diamond form this covalent network. You really, I mean, because they're so hard and strong and rigid in structure, they obviously are going to have high melting points. They're rigid, they're hard. Two-dimensional is not, I'm not, you don't even need to worry about it. Okay. I'm literally going to move on. Okay, here's some great pictures. Okay, here's the pictures I was going to look up. So here's carbon as a diamond. And over here, you have carbon as graphite, like what's in your pencil. It's not lead. And you see the diamonds, just look at how every carbon atom is, there's a network of carbon atoms. They're all attached to each other, right? And you can see that. I can draw it. You can see it. And no one's going to move very easily. But over here in the graphite, imagine you're writing with your pencil. And you can imagine that little, let's see, that little plane of carbon atoms coming across onto your paper. And then you write again and that plane comes across, right? And you write again and that plane comes across. So the way that these are bonded, and this unit has a lot to do with chemical bonding, okay? If you haven't figured that out. Ionic covalent, you know, we started with some of that stuff. I don't know. Polar, non-polar. So the way that these are bonded gives them many of the properties. So once these are your covalent network here, and it gives it very, very hard, very rigid, very, very, very high boiling point. That's all you need to know. That's all you need to know. I just wanted to bring it up. I would like to look at those in class. I would like to look at those in class. Solids, liquids, and gases. Let's just see here so we can finish this. So we don't need to make another one. Now, I mean, obviously you can represent the difference between solids, liquids, and gases. Drawing, like particles close together, a little further apart, way far apart. Yeah, I just, you know, I'm going to have you kind of look at that yourself. It's just so simple. I don't want to sit here. This constituent particles and liquids are in close contact with each other. They're continually moving and colliding, right? They have the ability to roll over each other. They are influenced by the strength and forces of, you know, they're in intramolecular forces. Such as boiling points, freezing points. Maybe this is that part of 3.1. Maybe it leads into this is that. The solid and liquid phases have similar volumes because they are in close contact, right? That's what we mean by constant volume. Wherein gases are going to expand. They don't have similar volumes. Gases are in constant motion, and there you go. What you see here is this is ordered, and the word amorphous means disordered, okay? Just a vocabulary word. So there you go. Crystalline means ordered, whereas amorphous means disordered, okay? You can have crystalline solids and you can have amorphous solids. That would be the difference. Continue, liquids, you know this. The solids and liquids tend to have the same volume. They're not expanded to any appreciable extent. Affected by the type of bonding, a type of intermolecular forces. So when we talk about solids and liquids, we talk about intermolecular forces. And when we talk about gas, we do not talk about intermolecular forces. Okay, so as I'm going to leave it at that. I just didn't want to skip it entirely. Okay, thanks for watching.